New engine designs have been solicited for an advanced trainer capable of replacing the T-38 trainer aircraft, which is currently powered by the J85 GE engine. It is the goal of this project to design a new engine starting with the GE J85 as the starting point, with an entry into service of 2025. The J85 was a single-spool turbojet engine designed in the 1950s during the advent of supersonic flight. Since then, a number of breakthroughs have taken place in the aerospace industry, including advanced materials capable of withstanding higher temperatures and stresses, higher turbomachinery blade loading, higher turbine inlet temperatures, resulting in shortened combustors, and lower specific fuel consumption due to advances in cycle design.
The point of the constraint analysis is to find the solution space where the aircraft can fly. The constraint analysis is used to find the thrust loading and wing loading for the aircraft. We want to find the lowest thrust loading and high wing loading for the aircraft. Low thrust loading means we need less required thrust for the aircraft. High wing loading means the aircraft will fly smoother. The design point is where the triangle is on the graph.
The goal of the cycle analysis is to determine the thermodynamic cycle parameters that meet the mission performance goals. In the case of this project, the main goal for the cycle is to keep the specific fuel consumption as low as possible while maintaining adequate specific thrust. It was decided to utilize a low bypass ratio turbofan design for this advanced engine, since it will greatly improve the fuel consumption while keeping enough air going through the engine core to keep the blade heights at typical levels and keep the specific thrust high. Many cycle trade studies were conducted to close on a final design point for bypass ratio, overall pressure ratio, fan pressure ratio, and combustor exit temperature. The final design yielded a 28% benefit to specific fuel consumption at the cruise condition.
The objective of the mission analysis is to find a relevant mission for the aircraft. In total, we came up with 11 segments. The cruise segment, as expected, uses the most aggregate fuel because that is where we are flying the longest. The supersonic dash segment has the most specific fuel consumption because they turn the afterburners on during that segment. A graphical view of the weight after each segment is presented. The purpose of the inlet is to bring free stream conditions to the conditions needed for the fan face. Supersonic and subsonic designs were looked at. A subsonic design was chosen because most of the mission is going to be flown subsonically. The losses of having a supersonic inlet flying subsonically outweighed the losses of flying a subsonic engine supersonically. The inlet is also very long because in the RFP it was stated that we required to fit the engine in the same cell that the T-38 has. Since the T-38 has a supersonic inlet on it, the inlet is very long. This requires our inlet to be very long as well. There is about a 1% pressure loss for our inlet.
The fan and compressor are components which take air at free stream conditions and prepare to enter the combustor by increasing the total pressure of the air. The design of these components is affected by the pressure ratio of the engine, the rotational speed of each shaft, the speed of the airflow, and the radii of the blades. The design was originally completed at the pitch, and by iterating on the radii and axial Mach numbers, we're able to complete a successful design. The flow path was sized and generated to allow decent hub-to-tip ratios in each blade, allowing for an easier design. A free vortex approach to radial equilibrium was used, and conditions at the hub and tip were fixed. The compressor and fan are mostly limited by losses due to diffusion, but through careful consideration of these effects, our design was able to avoid excessive efficiency losses.
Turbines are the driving force behind the gas turbine engines. Without the work they captured, nothing would move. They take hot gas from the combustor and expand it through the turbine blades, which catch the energy like a pinwheel and cause rotation. The speed of this rotation, RPMs, needed to be designed around limiting factors such as the fan's tip speed and the stress limits the turbine could handle, but still be able to work with both. To help us achieve creating a small bypass, we had to add stages to keep them from overloading in the low pressure turbine, and also to help reduce the Mach numbers in the high pressure turbine. The work that was required for this engine was very high per stage, and to allow for a bypass we had a limited diameter. This left us with few options besides adding more stages, but in return this made it easier to make our exit angle come out virtually straight.
Once the turbomachinery designers have set their constraints, the combustor design can be completed. The combustor burns the fuel and provides the temperature increase required to generate work in the turbine. The Bearcat 4000 chose a lean burning combustor design over more traditional technology. One reason for choosing a lean burning combustor was that it provides lower local noise, emissions, and aircraft fuel burn during dry operating conditions compared with legacy technology. Also, additive manufacturing has allowed for complex designs in the combustor liner to become cost-effective, allowing for effusion cooling, which are small hole patterns in the wall, to be used over more traditional film cooling. This has increased the life of the engine because film cooling is inherently full of thermal stresses. Due to major commercial engine development programs, we believe that into the future, commercial development will actually drive military engine development, and that by 2025 this technology will be fully mature and ready for military use. The combustor was sized to have an equivalence ratio between 0.6 and 0.7 in the primary zone, and the mass flow percentages were found accordingly and shown on the screen. The figure on the screen also gives some dimensions that were calculated using the Lefebvre design method. It was found that there would be around 9 swirl cups in the annulus. The flame is stabilized by a swirl cup consisting of a pilot for flame stabilization and a series of concentric pre-mixing fuel injection points in a main swirler, as seen on the diagram on the screen.
The purpose of the exhaust nozzle on a turbine engine is to accelerate the flow out the back of the engine to the appropriate velocity in order to generate thrust. It was determined for this engine that a convergent nozzle would be more effective, as it not only reduces the amount of complexity in the design, but also since the aircraft spends a vast majority of the mission at subsonic speeds. It is at these speeds where the convergent nozzle will be much more efficient. Since the engine has an afterburner, it was required to have a variable area nozzle. The exit radius of the nozzle was calculated for each flight condition and is displayed in the graph on the right.
In order to choose materials, we based our decisions off of what is documented in recent literature. It was decided that polymer matrix composites would be acceptable in the fan and would give us a weight benefit. Titanium alloys would be sufficiently strong in our compressor. The combustor would be made of ceramic matrix composites, allowing for decreased weight and high thermal capabilities. The HPT and LPT will be made of titanium aluminized to handle the thermal stresses and also to be strong enough to withstand the aeromechanical forces.
In conclusion, we conceptualized an alternative engine to the J85, dubbed the Bearcat 4000. It is a turbofan engine with a bypass ratio of 0.35, a total pressure ratio of 40, and a turbine inlet temperature of 2600 degrees Rankine. We were also able to demonstrate that the Bearcat engine met thrust requirements and improves fuel efficiency, with a 28% improvement in specific fuel consumption during cruise. Turbomachinery components were designed and verified using common metrics. A lean burning combustor was sized and conceptualized, and an 11-segment mission was developed. In addition, other components were also sized and evaluated.